As with any EtherCAT system, we're going to first start with setting up the servo drive for EtherCAT mode. We open up DMM drive software and connect to the drive via the serial port. We open servo settings, where all the drive parameters are being read automatically. For EtherCAT, make sure both the acceleration and the speed parameters are set to 127 and the gear number set to 16384, and put the drive into Ethernet mode and press save. After saving these parameters into the drive, power cycle the servo drive to make sure that it boots up in EtherCAT mode. We open up TwinCAT here and create a name for the project. We're going to call it TwinCAT Structured Text Motion Control Demo. Once the drive powers up in EtherCAT mode, it's going to be disabled by default. So we have TwinCAT loaded. The first thing we do is set our target to the IPC that's connected to the computer. And we put TwinCAT into configuration mode so we can scan the nodes for the servo drive. Open I/O devices and press scan to scan for the servo drive. Detected the device port, and it's going to scan for the I/O devices. And it's picked up the drive, and we leave that in NC configuration. We're going to run it the free run and activate the configuration. After the configuration is active, we can open up our numerical control tab and go into axis 1. And we see that the position of the drive is updating via the PDOs. Press set and all to enable the servo drive. We see that the drive and motor are enabled, and the position of the motor is locked, and we can jog around the motor from the commissioning tab here. So now the motor and drive are set up for EtherCAT, and we can move on to the PLC programming side. Once our axes is set up, we're going to first disable the axes. And we can add a new PLC program under the PLC tab. Right click, add new item, select standalone PLC project and give it a name. In this demo, we're going to be using all the internal MC function blocks in TwinCAT, so we have to first add those resources under the References tab. Right click on Resources and add that library. Open up the Motion tab. It's going to be under PTP and select TC2 MC2 and click OK. And we see that those resources are added. And we open up our main program. Then we can use our sample code and copy over all the functions that we need for power. This is the FB power function block that defines all the inputs and outputs. But before calling the first function blocks, we have to define the axes. And we copy over all the variables needed for the MC power function block. Here, we also define two variables to log the error and the error ID, which we will use later. So we first have to link the axes to the actual physical axes on the EtherCAT bus. To do that, we open up the Motion tab under Axis 1, double click on that, and go into Settings and Link to PLC. But before we do that, we have to activate the new configuration for the axes that we defined in our PLC code to be linked into the PLC. So after we have the configuration activated, we should be able to see our axes variable inside the link to PLC. And we select that and press OK. So now the code knows that the axis physically is connected to this axis reference. And we activate the configuration again to make sure the link is established. So right now, before we run anything, the motor is disabled. And we're going to build our PLC code. After it's finished building, we're going to log into the PLC. And we're going to run the program. The definition for the FP function block. For MC power, we predefined that the enable positive and the enable negative to be true. And the actual enable input for power, we're going to control manually. Open up the FP power dropdown. Under all the inputs, we're going to prepare a true statement into that input, and we're going to write that statement. And we see that the motor is now enabled. And the enable input is now true. Once we have our axes is enabled, we can move on to the absolute command, and we first disable the motor for safety. Once disabled, the motor shaft becomes free to rotate, and we log out. To send the absolute move command, we copy over the code as needed. We first copy over the function block. And we're going to link that to the MC move absolute command. To be explicit, we're going to set a variable called B execute move. So we can trigger this in our code using this variable. And we also manually set the buffer mode to MC buffered mode for smoothest motion. We build, log in, and run the program. You'll notice that all the axes is mapped to the same axes in our function block definitions. Before initiating the absolute move, we have to enable the motor. So once we write a true into enable input of FP power, we see that the motor is enabled. And and we're going to send the absolute move. To send the absolute move, we have to set the position and the velocity. The acceleration, deceleration, and jerk we can leave at 0, as TwinCAT will use the default parameters for these motion profile. We see that the MC buffered mode input is set to MC buffered according to our code. So we can set our position to 50 millimeters and set the velocity to 10. For this demo, we'll use all the default values of millimeters and millimeters per second. And we can trigger the move by sending a positive edge into the execute input. So to trigger the absolute move, we have to set the B absolute move to true, as we map this internally in the code to the enable input of the absolute move command. So once we run that, we can monitor the position of the motor from the MC axes tab, and we'll notice that the motor has run to 50 points absolute position. And if we change that to 200, and we write this into the PLC, and we toggle the execute move again, we see that the motor runs to position absolute 200 at 10 millimeters per second in the velocity tab, as we see below. And we see that the motor stops at 200 absolute position with 0 velocity as it's finished its move. After the absolute move, we can try a reset command input. Anytime during motion, whenever the drive is on and normal, we can send the reset input to reset faults within the servo drive. So to modify our code, we can log out of the PLC. We'll also monitor the FB power error bits to monitor any faults within the servo drive. So we copy over the code for the function blocks for MC reset. And we define this FB reset function block as the axes reference as the only input that we need. And we build, log in, and run the program. First, we execute the enable command to enable the motor again. We see that the motor is enabled. And to simulate a fault, we can disconnect the encoder cable from the motor to the drive. But before we execute the fault, we can monitor the error input from the FB power function block, and we see that there's no errors in the system currently. And as soon as the encoder cable is disconnected, we see that the error output from the FB power becomes true with the error code associated. So we can use the reset command that we created to reset the servo drive by setting a true statement into the execute input. As soon as we write a true statement into the execute, we notice that the drive is reset. The drive has reset, but TwinCAT reports a following error. So we have to toggle TwinCAT's reset input again to clear the following error. So once we toggle the execute input again, we see that the error has become false. And we can enable the input for FB power to enable the motor again for normal operation. So the next thing that we can try is reading the actual position and setting the actual position. So we log out of the PLC to modify our code. Reading the actual position reads the current absolute position of the motor and outputs it into a variable. And setting the position sets the current position to a predefined position of commanded. We copy over the function blocks as well as the variable declaration and mappings to the MC commands in TwinCAT. So for the reading position function block, we map it to the axes and we automatically enable it in the code. In the output, which is the position from the function block, we map it to lread position variable that we created. To set the position, we can do it all manually, and all we need to do is map the axes. So we build, log in, and run the PLC. As soon as the PLC runs, we can see that the position value updates from the read actual position function block. And the position output is being mapped to the lread position variable. We can see that the enable input for the read position is automatically enabled. The motor is already enabled from the previous example, so we can set and execute into the move absolute command. The power position of the motor is always 0. And we can send an absolute position command of 200 with a speed of 10, and we execute the move. And as soon as we write the variables in, the motor starts to run, and we see that the position is updating in real time, which is the same number as the axes tab. The motor will stop at 200, The LRead position variable can be used freely in your PLC control code. And we see that the motor reaches 200. To use the set position command, we open up the inputs and outputs of this function block. Let's say we want to set the position to 0, and we send a true command into the execute, and we write this variable. As soon as that position is executed, the position of the motor is set to 0, internally within TwinCAT. And for example, if we want to set the current position as 100, we input 100 and we false the statement. And as soon as we set it to true again, and we set this value to true, we see that the current position is set to 100. Next, we can try the velocity command and the stop command. So we first stop the PLC, log out, and copy over the code. We build, log in, and run the PLC. We can maintain our last state and the motor is still enabled from our last example. We see that the position of the motor is still at 100 and is continuing to update. For move velocity command, we can set the velocity that we want. Let's say 10. Again, the acceleration, deceleration, and the jerk is not necessary. And we true the execute. And we write that value. So the motor starts to rotate, and we can monitor the motor position and speed in the commissioning tab. We see that the velocity is 10 millimeters per second. The speed in this example is jumping around a little because the gain parameters are set to very low. Next, we can try the stop command. This is typically used for e-stop in emergency situations. We open up the function block and just toggle the execute input as true. And as soon as we execute the stop command, the motor stops its rotation or any type of movement. Next, we're going to do a torque control example, which is using the MC torque control command. So first, we copy over the code. We build, run the PLC code. The previous command that we sent in the last example was the position and velocity commands. Internally within TwinCAT, the position and velocity commands are handled under mode of operation 8. But for torque command, we need to use mode of operation 10. If we look into the PDOs of the drive, we notice that the mode of operation is always in 8 for position and speed commands. But as soon as we send a torque command, TwinCAT automatically switches the control modes to 10, which is the correct control mode for CST mode. So initially we can send a 0 torque command and we execute. But before we do that, we have to clear the stop execute from last example, which interlocks any motion control commands within the PLC. So we write a false into the execute of FB stop, and we toggle the execute in torque control. We're going to build, log in, and run the PLC. So the first thing we have to do is enable power to the motor. Right now the motor is disabled, and we enable the motor. And we check that the mode of operation is 8 as we've reset the entire program and done a fresh activate configuration. Then we can send a torque command of 0, and we execute that. As soon as we send the torque command of 0, we notice that the motor has 0 torque, so the shaft is freely rotatable. We can check that in the PDOs of the drive, the mode of operation has changed to 10, which is CST mode. To send a different torque command, we false the execute input first, and we can input a torque value of 5. Check the documentation of both TwinCAT and the DMM EtherCAT manual for the torque percentage reference. We can set the velocity limits to 100. And we write these values into the drive. So as soon as we execute this, we see the motor starts to rotate. We see under the PDOs that the motors are running, and the target torque is 50 relative to the command value versus a scaling factor. The torque actual value PDO can be used to monitor the motor. So we can use our hand to manually stop the motor, and we see that the torque actual value settles at around 50, which matches our command. If we let go of the motor and we let that run, and we stop the motor by sending a 0 torque command, we see that the zero torque command is executed and the motor shaft becomes free. We can also switch between different control modes or servo modes very easily in real time by just sending different position or velocity commands directly into the drive. Internally within TwinCAT, it will automatically switch to modes. If we send a position command of 1000 with a velocity of 10 and we execute that command, as soon as this execute bit is written, we see that the drive runs to absolute position 1000. And we can monitor that under the commissioning tab. As the motor ran at a certain speed, in torque mode previously, it'll go backwards into absolute position 1000. And we see that the mode of operation has been switched back into 8. The speed also follows our command of 10 millimeters per second.